Greetings, mathophiles. Welcome to a discussion of the concept of the sampling distribution from statistics. And the backstory for this is that we frequently have occasion to want to make inferences about entire populations based on samples taken from those populations, typically because to observe the entire population itself would be unnecessarily expensive or disruptive or intrusive or whatever. So we take samples. And based on those samples, we try to make inferences about facts having to do with the entire population. This process is called statistical inference. But the question of exactly what you can tell about a population from a sample is a somewhat complicated one. And so we want to delve into just a little bit of the beginnings of that discussion in this video. I promise there will be no formulas. This is going to be a strictly conceptual discussion. The way we're going to begin to try to figure out how to draw inferences from a sample about a population is to start with a known population, sample from it, and see what kinds of regularities might be observable so that then we can imagine maybe turning it around, sampling from an unknown population and being able to make judgments with some confidence about what the population is doing based on what the sample is doing. So our situation is going to be a simple one. We're going to imagine that we have a bucket with 10 balls with each of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to reach in, we're going to pull out a ball, we're going to take a look at its number, we're going to record that number, and then we're going to place the ball back, shake it up, randomize it, draw another one, and so on. So we're going to be sampling with replacement, and we're going to be sampling 5 at a time. So for example, I reach in to my bucket and I get a 9, put it back, stir them around, reach in again, get an 8, do it again, get a 7, do it again, get a 1, do it again, get a 3, and then I have my 5 values and I write them all down and I find their mean. And their mean, as it turns out, is 5.6. And so what we're going to investigate is the behavior of means of samples of size 5 taken from this population in this fashion. So I grab another 5 with replacement. I find their mean. I grab another 5 with replacement. I find their mean. And once I have enough of these means, I can start to look at how they behave. I can graph their frequencies. I can find the mean of those means. I can find the standard deviation of those means, and so on, and try to begin to understand the relationship between the characteristics of the population and the characteristics of samples taken from that population. Let's start by looking at the individual balls themselves. If I'm truly randomizing, if the balls are sort of indistinguishable by feel as I'm reaching in and pulling one out, then the probability of any given one of the digits on any given draw should be 1/10, right? This is what's called a uniform distribution. All of the outcomes in the sample space have the same probability. In this case, that probability is 1/10. If you know something about distributions of probabilities, you'll know the meaning of what I'm about to say. And if you don't sweat it necessarily. You can still get the main concept without having that background. But the mean of this probability distribution, the expected value of this probability distribution is 4.5, which should surprise no one given that we need to land sort of halfway between 0 and 9. The standard deviation of this probability distribution is 2.87. And we'll have occasion to compare that with some other standard deviations as we go forward. So you'll see on your screen the results of 10 of these repetitions of these samples of size 5. And I will make a graph of the frequencies of those means, of those samples of size 5. And you'll notice that the shape of that graph is not the same as the shape of the original probability distribution. It's not uniform. It's begun to clump a little more towards the middle. If you find the mean and the standard deviation of these means, the mean is about 5.06. Standard deviation is about 1.42. So the mean of these means is in the neighborhood of, but not identical to, the mean in the population and the standard deviation of these means is somewhat smaller than the mean in the population, 1.42 as compared to 2.87. So right away, we see a couple of things of importance. The behavior of the means is not identical to the behavior of the original numbers in the population. And this is a very important fact because it should cause us to be cautious about the inferences we draw about the population based on the sample, because the sample may not necessarily capture exactly what the population is doing. You can get gadgets to take these samples many, many, many times with next to no effort. I'll place the code for a TI-84 calculator program in the description to this video, and you can try it out if you'd like. But any kind of decent statistics package, spreadsheets, you can do these simulations very easily if you have access to even what's regarded as fairly minimal tech these days. So what I did was I used my calculator to gather 100 samples of size 5 from this population. And what I saw when I did that was, again, the same sort of clustering towards the middle. Mean of those means, all 100 of them, was about 4.59, so in the ballpark of the mean in the population, which was 4.5. Standard deviation of these 100 means is 1.34, which is, again, smaller than it was in the original population. That was 2.87. Now I'll ask myself the question, what happens if I take a sample of a different size? So instead of grabbing 5 and finding their mean, I'm going to grab 10 and find their mean. And I got my little simulation to do that 100 times. And what I saw was an even stronger clustering toward the center. I saw that the mean of those 100 means was bang on 4.5, which is the same as the mean in the population. I saw that the standard deviation of those means was about 0.89, which is less than in the population, and in fact also less than was the case with the smaller samples. So the main conceptual takeaways: the samples have a probability distribution. That probability distribution depends on the distribution in the population, but it is not identical to it. It seems to be the case that the means vary less than the original values from which the means are being drawn by means of a sample. It seems to be the case, and this is not a ton of evidence, but it suggests, points us in the direction of the notion that bigger samples vary less. And the study of those relationships is something that we will leave for another time. Happy mathing.